Good evening, everyone. Have you heard about the road traffic collisions that happen around us? Is there any way we can prevent such mishappenings? Well, AI can help us in configuring the predictions of such misfortunes, and we will get to know about it in today's session about predicting road traffic collision severity for the improvement of highways. To give a brief session about what the agenda is, we have Mr. Rich Gregson with us. He has been working in the data field for 10 years in both public and private sectors. He made the move into machine learning in 2019 and has worked on numerous projects in computer vision and natural language processing. And he recently engaged in DNA classification projects. Mr. Gregson is proficient in all data science stages, including data pre-processing, statistical method application, predicting modeling, data visualization, and result communication, and is currently a data scientist at leading tech company. Mr. Gregson believes machine learning and artificial intelligence will continue to shape our world for the good, and because of this, he wants to help and support people entering the world of machine learning and now allow them to make a real difference. Welcome, sir.
Thank you very much for the introduction. It's my pleasure being here. So what I'm going to do over the next hour or so is we're going to take a look at what the project entailed in terms of building an end-to-end solution for predicting road traffic collision severity. We're going to talk about all the trials and tribulations, what worked, what didn't work, and any future modeling that we can do to improve on what we discovered. The project that I'm going to talk about was done through Omdina, which is a online collaboration platform where people from all skills, all backgrounds, skill levels can join and work together as a team on creating solving a problem using machine learning, data science, data analytics, whatever that may be. So I am just going to share my screen and get started with the presentation. Okay, so this is the table of contents. I'll probably skip who am I because I've just had a fantastic introduction, so I won't need to do that now. We'll talk about the project structure, the two data sets that we used, and we'll take a look at some of the attributes that we found in the data set from the exploratory data analysis. And then we'll move on to the predictive modeling. And what we'll do there, we'll talk a bit about what we attempted to do, and then we'll deep dive into the code so you can see how we did that. Now, don't worry if you're new to coding or you don't have any experience in coding. I'll tell you what the code does, and it's not necessarily important that you understand what's happening. It's the output that is most relevant. And then we'll take a look at the solution that we put together and any sort of ideas we've got moving forward. And then we'll have a bit of time at the end to do some to ask some questions and whatnot. Okay, that's me. I've already had a wonderful introduction. So the project that we decided to do, I'm the chapter lead of Omdina Liverpool, and in the UK, we have, a very aging road infrastructure and road network. Now, the deaths on UK roads have had a steady downward trend since the 1960s. However, in 2020, there was around 1,500 people who lost their lives on the UK roads. That is still quite a significant number. So what I wanted to do was basically see if we could gather some insights through a data science pipeline to try and approach local government jurisdictions, try and identify what is going wrong, why are these people being killed on the roads, and can we offer any insight to help them improve the road networks. The task we decided, because the data was so rich that we were provided with, we split the task into 4 pipelines. So we had the number one pipeline, which is to predict the road traffic collision severity. We could plot a geospatial heat map or just a standard geospatial map with all the accidents on, so we could see where these accidents were happening. We also have a time series analysis model, which could give us a prediction of how, what the trend is going to look like in the future, in the next couple of years. And then we were looking at a vehicle analysis and perhaps a prediction on what kind of vehicles were most likely to get into a road traffic accident. So as this project was designed for beginners and intermediates, I wanted to show the students who enrolled on this project what a real data science team looks like. So as you can see here, I constructed a number of different pipeline groups, starting with the data engineers. Now, there were 3 data engineers, a lead data engineer and 2 co-lead data engineers. And what they did was take the 2 data sets, the accident data set and the vehicle data set, and they prepared it into 4 different pipelines, each suited for this particular task. And then those the data science leads in these pipelines would then start building the model here. So this is what the project timeline looked like. Week 1 was data pre-processing. Week 2, exploratory analysis. Week 3, feature engineering. Week 4, model development and evaluation. And week 5, model deployment. And I've spelled deployment wrong. And the final presentation. Now, this is a very constricted timeline. In real life, the data was so rich, we could have spent months on this project. But what we like to do is give people, a month or so of working on a real life project with a real life team, and they can use this project and each step of the way as part of their professional portfolio. Each task had a task lead and co-lead. The task lead was someone who may have, an intermediate to expert level of experience in data science. And the co-leads were people who were beginners, maybe know how to, rudimentary code Python, and, just not someone who is very experienced, because that is their opportunity to learn and about how to manage a real task. Everyone else in the group who wasn't assigned to a task lead or a co-lead could work on anything they wanted to. They could jump in any part of the pipeline, what interested them. If they wanted to do the exploratory data analysis for the prediction, the severity prediction, but then wanted to do the feature engineering for the time series analysis, that is absolutely fine. And it was a great way for everyone to learn different models, different approaches, different sort of techniques for each particular output. Okay, so the accident data. This was the main data set which was going to be used by 3 different pipelines. And every line in that particular file represented a unique traffic accident, and it was identified by the accidents index column. There was around 40 to 50 features in the data set, and the date ranged from 2005 to 2017. And there was just over 2 million records in this particular data set. Now, each pipeline done their own exploratory analysis. And as you can see, we've got a couple of charts in there, which basically, as a result of each individual pipeline's, findings. So one of the big takeaways that we found was that the severe and fatal accidents seem to have almost an identical representation in terms of feature information. So there was very little, if anything at all, to determine the difference between a severe accident and the fatal accident. And I'll go on to in a little bit more depth about that later on when we look at the code of the modeling and whatnot. Okay. So there were some interesting outputs on the accident data set over the Christmas period, the Christmas holidays from about November to the end of December. There was a 19% reduction in road traffic accidents, slight, severe, and fatal. On the UK bank holidays, which usually about 5 every year, and they run between 1 and 2 days, there seem to be significant increases in road traffic collisions during that particular period. And we sort of surmised that people are off work, people are off school, there's just more vehicles on the roads, which may lead to obviously more accidents. The vehicle data came from the same source, the UK Government Department of Transport. The vehicle data was much smaller. And what this basically compiled was every vehicle involved in an accident, and it used the accident index, and that was the primary key, which could be matched to the vehicle data as well. The problem with the accident index, it was duplicated in the vehicle data because more often than not, there's more than one vehicle involved in a road traffic collision. I think the most we had was 58 vehicles involved in one accident, and that was traced back to a motorway or freeway, however you say it, pile-up, and it was multiple casualties and multiple vehicles collided, and that was quite a that would be seen anywhere else in the distribution. That might have been an outlier, but this event actually took place, which is quite scary. The data for the vehicle data ran from 2004 to 2016, so a slightly different distribution, but that was all what was available from the Department of Transport, and it was about 1.6 million records. And as you can see, again, we've done some very in-depth EDA, and these are just some of the highlights with some of the key takeaways here. So this one was quite interesting because these are the reasons for the vehicles being on the road. So you can see other and not known are big ones. Now this can be put down to some of the accident reports are actually self-serviced. They're not police reports. So people would have a slight accident, a little knock in the road somewhere, and they would go online and fill out a accident report form. The problem is with that, when you compare it to the police reports that have been filed by the police reports are much more robust. There's no, very little missing data, if any. But when you're left, the general public, we do have certain anomalies like this. So not known. That was that's just one of the products of the simple fact that these people didn't fill them out. Other than that, though, journey is a part of work, so the commute was a large cause of traffic, and that sort of correlated around the date and time, the days and time of the accident data. Days through the week concerning the hours between about 7 in the morning till about 9, and in the evening about 4 till about 6 seem to be have a little peak in accidents. So we can see that. So business and there's the commuting, and the journey also includes business travel as well, not necessarily to work, if you're visiting other people, other clients and whatnot around the country. Okay, the key takeaways from here, most of the drivers aged 26 and 35, urban areas, most of the vehicles involved were made by Vauxhall, and that was simply because Vauxhall is one of the most popular vehicles on the road in the UK. So of course they're more likely to be in an accident more than any other. Okay, so the next part, we've cleaned the data. We've done some EDA analysis and pulled out some very interesting observations. And we've done some feature engineering around these observations in terms of separating dates into times, into hours, because especially for the time series analysis, that is a very useful sort of part of feature engineering. The predictive modeling was evaluated on 2 different versions of the data set. The accidents-only data set consisted about 1 million rows between the dates of 2005 and 2010. We didn't use the whole data set, and the reason is because once we train a model on the 2005 and 2010 data, we can validate and test that data on 2011 to 2017, and we can see whether or not the model is effective. And we can also start to troubleshoot and see if the data is there any sort of obvious changes in statistical distribution of the second portion of the data set between 2011 and 2017. Also, the accident data combined with the vehicle data. Now, because they were from 2 slightly different time periods, we ended up with 600,000 entries, which could be matched by the accident index. And this combined all the data from the accident data and the vehicle information as well, and information about the driver. So it delivered a very robust and detailed amount of data. The models we tested initially are listed here. So we've got the decision tree classifier, the random forest classifier, adder boost classifier, KNN, support vector, and light gradient boosting and extreme gradient boosting classifiers. So at this point, I'll take a look at the code that we did for the modeling. This was the main modeling form and notebook, sorry, not form. And this was where most of the modeling was done. However, within the group, a number of different people tried various different tactics that were discussed as a group. Some of them, were not very fruitful, so we sort of left them behind. Some of the testing with the likes of the KNN and the SVM models, they didn't really work out very well, so they were pretty much dropped. But as a group, we experimented with a lot of different techniques. This particular notebook gave us the most hope in terms of the most powerful outputs. But as you'll see, can these results be relied on? We'll get into it. So the first part of this code is basically importing all the essentials that you will need: pandas, numpy, matplotlib, and seaborn. You've got your data frame manipulation, your mathematical manipulation, and your plotting tools. And we also, at this point, bring in the train test split. So we're loading the data, the vehicle data, the accident data, and the accident's full data. So this vehicle data is between 2005 to 2010. The accident data is the vehicle data is from 2004 to 16. The accident data is 2005 to 2010, and then we have the full data set from 2005 to 2017, and that is what we were going to validate the modeling on. So this piece of code here is basically replacing some of the missing values as just unknown, because even though they're missing, they've been either left, they've been left out for a reason. These are some of the data is self-reported, and it would be, if we were to drop it, we might lose information, is basically what I'm saying. So that was changed to unknown, and that means we can then encode it and, see if it offers any value whatsoever. If not, we get to a point where it doesn't offer any value, we can just drop it. We know we can do that. And it's the same for the accident full as well, data missing or out of range. Until we take a look at, on how these attributes are, what they're delivering to the model, it's probably not advisable to drop them in the first instance. Let's see how they react first, and then we'll make the decisions to fine tune our model. Okay, so this particular code is just making sure, seeing what unique values we have in our data, and we repeat this step for a number of each particular data set. This one was a little bit of feature engineering, as I mentioned earlier. I've brought it over into this notebook just so you can see, and it was just splitting out the time by the date, the month, the time, the hour, and then checking, what sort of data types do we have within our data set. And as you can see, it's a mix of categorical variables and numerical. And we do the same for each particular data set. And we just double check, what the data types are, what the unique values are. So we understand what we're working with. At this point, we have to encode them. Machine learning models, they like numerical data. As it's a classification problem, the accident severity, we can leave that as categorical because we do amend that and we encode it numerically later on, but it's still treated as a categorical variable. So as you can see, running this code here is basically encoding using the get dummies, which is very pandas method, which is very similar to one-hot encoding. It creates a binary classification for it, basically. Well, not binary, but it assigns numbers to it. Okay, and then just to bring your attention to this line of code here, this is encode the full amount of data is being encoded. So that's the 2 million lines, and we've just extracted everything above the 2010 mark. So we know our encoded full data set is a different distribution, 2011 to 2017, which is very important, as you'll see in a moment. Now, this is changing our categorical variable, the target variable, accident severity, into a code form, a numerical form. And that brings us to the modeling. So the first part of the modeling was done on the 2005 to 2010 data. And we split that data into a 15% portion for the testing data, and the rest of it was for training, and a random state was set at 22. And what we've done here, we brought in a couple of classifiers and we've assigned them to a list and left them pretty much, with very little, if any at all, hyperparameters, just to, get a sort of baseline of, to understand what we're dealing with in terms of our data. Now, this big block of code here might look intimidating, but it's just basically a for loop which runs through each of the classifiers that were mentioned in this particular list. It applies the training data to each of the models and it runs them. It makes a prediction. It records the best accuracy. It records the best model. It makes a note of the train time, the prediction time, and it gives an accuracy score. However, when you've got a when you've got a classification problem, especially a multi-class one, accuracy isn't probably the best metric. You need precision, recall, and the harmonic mean between the two, which is usually known as F1 or F beta. We built once it's made its prediction, it's been trained and made its predictions. It puts the results in a confusion matrix, so we can easily look at how the model is performing and make sense of what it's trying to do. And then, as I mentioned before, we've got the positive predictive value calculation here, and what that's telling us is basically keeping account of true positives. So what the model has predicted, are they actually correct? And what's the percentage of them correct? True, what's the percentage of those true positives? So when you run that code, we get an output like this. So it gives us the model, it gives us the training time of that model, prediction time, and the accuracy score. The accuracy score, 74%. That isn't bad, you may say, but when we actually look at where it's making these predictions, 0 is is slight, 1 is severe, and the fatal accidents is 2. Now, when you take a look at the confusion matrix, it doesn't seem to be, it's lumping them all in the slight. The slight class accounts for 85% of the data set. It's massively unbalanced, and we can see that. Now let's look at the positive predictive value. It's getting the slight 86% correct. Every time it sees 86% of them are marked correct. That's how many exist in the data set. So even if it predicted slight 100% of the time, it'd still have an accuracy of 85%. It's meaningless. And as you can see here, it's struggling with the serious and fatal, and it's not far off their sort of numerical representation within the data set. So it's no good. The random forest classifier, it just bottomed out. It is not great at all. Again, it's just guessing. If it gets to the 100%, that's what it's going to get 86% of them right. So them results are quite useless. The adder boost as well, same story, but it doesn't even predict any fatal correctly. And then we have the LGBM classifier, same story, not great at all. It's struggling. And funnily enough, the king of tabular data, XGB boost, is the same. And then the best model for the best accuracy was 85%, but we already know from looking at its decisions, it's not reliable whatsoever. It's not making any good predictions. Okay, we'll come back to that now. So let's try modeling for the 2005 and 2017 data set. Now, if you remember, this is the data, the accident data and the vehicle data that has been merged together. And again, we do the same sort of feature engineer in terms of date and time. We get the dummies, we basically encode them into the numerical format, and also do the same for the outcome in a category. So it acts like a category, but it's represented as a numeric value. We split this data, and again, we run our block of code. Now, in real life, this block of code is quite messy, so you'd probably create a function. But because this project was aimed at beginners, we want to show the entire code in its raw format, so people get a more intuitive understanding of what we're actually doing. When you build everything, what I've found is when you build everything in functions, it can be a bit intimidating for beginners. So it was advised, let's just do it raw, and then we can refactor the code later on. That's not a problem. So again, we run the same block of code and we get the output. So again, it seems that the model is doing the same thing. It's not being able to identify the decision boundaries within the data. It's pushing more to the majority class because it knows, well, it doesn't know this, but it's basically, if it guesses, there's going to be a significant amount of accuracy. So again, we are foiled by the unbalanced data set, and it's the same for every model. And if we take a look at the best model for the vehicle data, the accident data, sorry, it was the LGBM, and it's the same story with the combined data as well, the merged data. So what are we going to do? The classes are unbalanced, completely unbalanced, so we're going to have to attempt to balance them. And the first method we use is something called random undersample. And what it does, it takes a look at the minority class, which in our case was the fatal accidents, and it was only represented in a million rows. It was represented by 14,431 instances. So what this does is randomly take from the majority classes and samples them to equal the same amount as the minority class. So as you can see, we've got slight, severe, and fatal, all equal. So fingers crossed, we run the code. The model can make more sense of it because it's not being pulled, its decisions aren't being weighted anywhere else. It's not being overwhelmed by an overwhelming majority class. So we run it. And as you can see, the accuracy has fallen to 41% in this decision tree classifier. But let's take a look at what really matters. The confusion matrix doesn't look, it seems quite random. Everything seems to be, it's not shining in any particular classification. And then if we take a look at the positive predictive value, it makes more sense. But it's 44%, 43%, 37%. It's not, it's not even as good as a flip of a coin at this point. So let's have a look at what else we've done. The random forest classifier. Again, a little bit of an improvement on the decision tree. but not much at all. The boosted classifier, same story. The LGBM classifier, let's see what's happening. Same story. And again, nothing too overwhelming here, nothing too convincing. So let's take a look at the confusion matrix of XGBoost. Again, not much going on there. So, okay, let's try something else. We'll use the class balancing using SMOTE, and I'll talk a bit more about SMOTE in the presentation, but let's just take a look at the code for now. And what SMOTE is doing is it creates synthetic data to boost the representation of the classes. So as you can see, let me just go back up a little bit. We run the same code again, so we split that down. And as you can see from this graph, the amount of predictions it's making, it's a lot more because there's a lot more data because we've synthetically derived some. So let's just take a look. The accuracy score has gone up to 86 on the decision tree. So when we take a look at the data here, it looks really good. If you see all these ones here are true positives. It's classified slight, it's predicted slight, and the actual outcome has been slight. Good news, and it's done this all the way. And as you can see here, the positive predictive value, 85%, 80%, and 95%. Fantastic. The random forest classifier, even more so. It nearly predicts every single fatal accident with 100% correct. So we take a look at the others. The others are a little bit worse. The boosted trees are a little bit worse on this one, and there's plenty of reasons why, but we've got some decent results, much better than they were before. So okay, so what we've done is we'll put this to the test. We'll test it in two ways. We'll test it on non-synthetic data, so the original data set, and see what happens. And then we'll test it on data that it hasn't seen from a different distribution. So this code here, we basically saved the best model as was defined up there. So it was the random forest classifier with an accuracy of 93%. We used the data that we used before, but that hasn't been synthetically undersampled and it hasn't been through SMOTE. It's the raw data that we train the baseline model on. So we split it again, we load it in again, and this time we load the model and we have the loaded model that was trained on SMOTE data make predictions. And then as before, we classify this and we use a classification report to see what's happening. So the data that hasn't been synthetically derived, we take a look, great results. We take a look at the test performance, the precision's high, recall's high, and the F1 score, the harmonic mean between precision and recall is also high. Great news, or is it? The next true test was to test on a new distribution, because let me just explain, we're testing on data that it's already seen. So the model has already made determinations about this particular data. So if we were to test it on this data, it would overperform. It's not reliable. If our data was completely static and this was the only data we had, that's absolutely fine. But in real life, more data will come, and this model will be we'll have to predict on data from the future, new data that comes in every day from police forces and from local councils and whatnot. So these results are pretty much worthless. They look great, but they're worthless in real life. So let's test it on a new distribution. We do the same. We bring in the encoded full, and if you remember, we only took 2011 to 2017. We load our SMOTE trained model, and we have the SMOTE trained model make predictions on the new distribution. We plot the same information as we did before, so we can see what's happening. And look what happens. We're back to square one. It's gone back to given all the weight to the balance, the overwhelming class. So it hasn't learned the pattern between slight. It hasn't learned between slight, serious, and fatal. So it's still relying on the numerical weights of the the particular data set, and this is also apparent in the precision and recall and F1 score. Now we did the same with the SMOTE for the merged data, but we didn't have a new distribution to test that on. That is something that some of the people, I mean, the task has ended, but some of the students on there really enjoyed the project, so are taking it a step further, which I'll go into a little bit more later on. So that's what, that's where we got with the modeling. Let me just jump back to my presentation. Okay. So these were our benchmark scores that we've seen in the code. Very poor on both data sets. We use the class imbalances, so the random undersampling balances all the classes by randomly removing entries from the majority class. The synthetic minority oversampling technique, or SMOTE, balances the classes by randomly generating new minority entries using a KNN model of the data. And we've seen when it's trained on that and it looks at the original data, it performs well, but that is most likely to be due to data leakage. When it's tested on a new distribution, the model falls down again, and we're back to square one. So the predictive modeling, when we were doing the EDA and we got to this point, the predictive modeling, we needed to understand what was the issue with our data. Why wasn't our models picking up any sort of patterns within the data that could definitively find, definitively class the severity? And one of the sort of ways of experimentation, what we're going to try is the group shuffle split rather than random splitting. And that we could maybe split the data in by year and see if there's any sort of patterns that can be recognized in a temporal sense. And also what we tried was an attempt to make the problem a binary classification. So merging the severe and fatal accidents together and see if the model can tell the difference between slight, severe, and fatal combined. We ran into the same sort of difficulties. The model was greatly struggling to try and to make decision boundaries between the outputs, and I'll talk about that a little bit later on when I show you the solution. So the next sort of stage, future work that may benefit the model, may make more sense of its results, one of the ways would be calibration. And calibration basically is calculating the probabilities of the model's outcomes and comparing them to the actual event rate of accidents. So it's sort of like a base rate. You compare your model to the base rate and see if the predictions make sense. And one of the most effective ways to calibrate your model is using something called isotonic regression. And what that does is basically tries to bring the predictions in line with your base rate. And as you can see here, if you these examples here are before and after isotonic regression, and this is applied on an SVM model. It's not something that we did. It's just from a paper describing isotonic regression. And as you can see, if your slope and intercept create this pattern or that pattern, this underestimates risk and this overestimates risk. It's used very much so in the medical industry, but I think we may gain some insights out of applying it to our own model if we take into account the true background rate of accidents. Okay, so the time series modeling part, we're not going to jump in too much because the time series modeling part was more built around a demonstration and a something for beginners to learn. It is quite a complex task, but when we completed the time series modeling, it didn't give us any new sort of insights. We already knew there was a downward spiral in the accidents overall, and it confirmed that. However, it was great fun putting it together, but we didn't really want to give out obvious results in our solution because we know it was something that we knew beforehand, but it was great practice for the beginners and experienced and intermediates alike. It was great fun. As you can see, we produced some fantastic some images for our solution. Okay. Now this is the front page of the solution. I'm going to launch it in a moment. Let's just get that done. So we built the solution on a Streamlit app, and this is what the code looks like for that. And we had a lead on the Streamlit app, OAS, and he was helped out by a guy called Kevin as well, who was also part of our project. And they built this together. And what Streamlit allows is a sort of combination of HTML and Python to build a interactive dashboard. The tutorials on Streamlit are absolutely fantastic, and it's really good for beginners to actually be able to deploy something. So let's run this model. We'll run this dashboard. But before I hit enter, let me just explain what the structure is. So you've got your assets, which are your images used on the dashboard. The data is the back-end data, what it uses to display what it needs to display. The pages, so we've got you've got a home page, a visualization page, and an about page. And we've got a README and the requirements for running this particular dashboard. Okay. So if you run that, we type in Streamlit run home py, and it should attach to my local host, and it'll bring it up in my web browser. So let that just load up. Okay, so this is the dashboard for our solution. And what we've done is basically have I'll go through the next couple of pages here, but in the main page, we've got a interactive map, and it plots out all the year and the accidents that happened in that year, the number of casualties, and whatever severity status that you pick in these options here. So let's set it to Liverpool, where I'm based, because I want to explain a little something about some of the reasons why our predictive model didn't function the way we thought it would. So let's go to the fatal accidents. If I just scroll down a bit, and let's move it down here. Right, okay. And we're going to zoom in a little bit. Is this, okay, let that load. Okay, so I live in Liverpool, and I live around this area here. Okay, and this accident, oh wait, there wasn't that one. Let me just zoom in a little bit more. Is it this accident? Yeah, so this accident happened probably about 30 meters, maybe a bit more, about 50 meters away from where I live. And it was an 89-year-old guy who had a few drinks in a pub. He was walking home, and he walked out into the road, got hit by a taxi driver who also happened to be under the influence of drugs, and he died. So my point of telling you this story is the fact that there was no problem with the road infrastructure that caused that accident. That accident was the result of alcohol, drugs, people not paying attention. It wasn't to do with the infrastructure. And what the Department of Transport provide about their accidents doesn't necessarily describe any of the underlying circumstances to the accidents. What it describes is where it was, what the weather was like, how old the driver was. It doesn't, it doesn't show us, it doesn't tell us the story of what happened. And so when I seen this little fact, I thought, okay, then, so what the distribution of fatal accidents, what can be put down to a genuine accident, which has nothing to do with the infrastructure? So I looked in Liverpool, probably looked at about 5 to 10, looked at other places, 5 to 10 fatal accidents. And I was able to sort of backtrack them on local media websites and stuff like that. And around 60% of them were due just because of accidents, people not looking before they cross the road, people pulling out on one another or whatnot. It wasn't to do with a fault with the infrastructure, if you know what I mean. So the data we use to predict severity only captures an iota of the circumstances behind each particular accident. So a machine learning model will greatly, to try and predict what the outcome would be. There just isn't sufficient data there, and that's why the model struggled. So, but what can we do about it? What can we do about it? So this data is publicly available on the internet, and that's where I procured the data and set it up for the task. Now, if we were working with the Department of Transport as our client, we would need to go back to them and their data engineers and basically say, this data isn't robust enough for what we need as an output. We have to go back to the business question. And that is the main problem we had. The stories behind the fatal accidents and the severe accidents are not truly represented in the data that's provided by the government. Now, this, gives us two outputs. Are we going to solve our problem using machine learning? No. We threw the absolute book at the problem, but the age-old saying remains: garbage in, garbage out. Unfortunately, our hands are very limited in what we can do. We can't just, we're not working for the Department of Transport. This was just a beginner's project. So we can't make any more amendments to this data than we already have done. We can't get, accident reports with this level of detail, only because there would be sort of, like sort of privacy issues around it. We would need clearance to get the sort of accident data that we would really need to make an effective model. However, is this project a complete failure? Absolutely not. Sometimes, especially in industry, sometimes the best answers and the best insight are derived from good old-fashioned data analysis. And that's exactly what we've done here. So this particular app that we've built is still a work in progress, because the people who have contributed to our project have dedicated their time, their knowledge. They've learned things. They've built a number of notebooks and explored our data. I think there was around 30 active participants, all contributing their insights. So this app is not only something to present, at the end of the project. This is also going to be a massive part of these individuals' portfolio. So this is, the project has ended, but we're going to develop this further and make sure it will help in the future career. It will help them land employment, and it will help their, it's evidence that they've been part of something and worked as a team and, ran through a complete data science life cycle, which was an iterative process. And when things went wrong, things didn't go the way we imagined, we were able to at least derive some interesting insights that could answer the question, how are we going to reduce road traffic collisions on our road, on the UK roads? So if you take a look at the visualizations, let that load for a moment. This is a work in progress. But what we can include is the accident counts, and we've done this through Plotly. So as you can see, again, the trend is slightly down, is coming down. Serious accidents goes up a little tiny bit, and the this fatal ones, go down, but sort of are at a plateau around here, which we've seen in the time series prediction as well. However, what that says to us is that, since the 60s, we know that the road, the accidents have been coming down year on year. So combine that information, what we've observed within our data through EDA, and combine that with actually analysing individual accidents that have no, the condition of the road network wasn't anything to do with it. We know that local authorities are already trying really hard to reduce these accidents. So the future of these accidents are genuinely going to have a lot of randomness associated with them. And that is going to be if the data stays the way in its current form, that's going to be a major problem for any sort of predictive analysis, and whether it's machine learning or whether it's time series. That is going to be quite an issue. Further to this, when we've looked at various scientific research papers that were attempting to do what we did in our project. However, they've obviously been assigned to various educational establishments and had their studies published. They ran into the same sort of issues. The data that's provided by the government in its current state isn't good enough for machine learning modeling, because it just doesn't capture the nuance around these accidents. So all we can offer is robust data analysis and make suggestions. So we've only got a few here at the moment, but some of the insights that we derived were most vehicles that were involved in accidents over the period of 2005 to 2017 were 7-year-old vehicles. We knew the same, the age of the drivers were generally between 25 and 35, and they were male. Now, this all matches up to the UK vehicle insurance information as well. Excuse me. The prices of vehicle insurance are higher for males, especially in the 25 to 35 category, because this data is already been out there, and we can already know who are most likely involved in accidents. The insurance information that we cross-referenced to also states that most of the accidents happen either driving for work or driving to and from work. So if you fill out your car insurance in the UK and you put down you use your car for commuting and business purposes, you get a higher premium because this data is already known. So the biggest sort of one was, as I mentioned, was the 7-year-old car. There was, I think it was around 40 to 50% of the data that we had was because of vehicles that were of 7 years age. So what further insights, further research is needed within this? It's a 2 million line data set with plenty of features. We could have spent 6 months pulling out information from this, but so we went with a high level overview. But the likes of having a 7-year-old vehicle seem to have most collisions based on the data we had in that particular time frame, 2005 to 2017. What makes a 7-year-old car necessarily more dangerous? Why does it represent most of the accidents in the UK? It's these sorts of questions that we can pull out of the data. I'm not a mechanic. There might be mechanical reasons for it. It might be, an age cohort of why who are driving these 7-year-old cars. But it seemed that was the key figures: a 7-year-old car, 25 to 35, and driving for work, business purposes, or commuting that was causing the biggest issues. Now, does this information, do these insights help the local government improve their roads? No, they don't. However, we do have various different information contained within the data where most of the accidents happen, and it seemed to be around the single majority class was the 20 meters away or further from a junction. However, the next three categories in that were getting close to a junction or at a junction. And if you if you combine those three data points, it would far oversee ones that people that crashed away, 20 meters and beyond away from the junction. So it is an interesting point. That basically is saying that the accidents that are happening, it's mostly coming up to junctions. So there still is work that we can make suggestions based on a geospatial map, and based on robust data analysis, we can still go away and say, in your particular area, there seems to be most accidents happen around this particular junction. It might be worth you looking into that. And all these insights will be available on our solution dashboard. Oh, sorry, I thought I was in the dashboard for a moment then. Let me just go back to it. And it'll all be available here, and we can obviously package this and send it to local governments, local councils and local jurisdictions as well, and they can look at our information, and they can basically derive their own insights and see if they can put anything into action about what we've seen. The most beneficial will probably be the geospatial map, because we can see the amount of accidents, where they're happening, where the hotspots are, and the longitude and latitude on the data that we had is very, very precise. The accidents I mentioned before about the 89-year-old guy, that is literally to the pavestone of where it happened. So there's no sort of ambiguity around where these accidents are happening. So it's very useful for a local government. So say if they're receiving 5 accidents a day in their particular jurisdiction, and 2 of them always seem to be around this particular junction or whatever it is, they can identify that very easily using our filters that we had and the supporting visualizations. Okay, and that brings us to any questions about what I've gone over. Let me just get back into our call. I haven't been able to look at the chat or anything like that, so if you did have any questions, please pop them into the chat. Oh, it's turned off for this meeting. There is a hand raised though.
Yeah, so anyone who has doubts regarding this session can raise their hands, and then we'll unmute their mics, then they'll speak their doubts to you.
Perfect.
So guys, if you have doubts, please raise your hands. We'll be giving you access to your mics very soon.
22 BCG 10178, you can ask your doubt. I have given access to your mic.
BCG 10178, are you there? Okay, let's just keep him at hold. The next is 22 BSA 10143. You can ask your doubt.
I think I might have bored everyone to sleep.
No, the session was quite interesting. I'm sure they must be here. 22 MIM 10125.
Hello.
Hello, we can hear you.
Yeah. So I'm asking, how can we learn to code? You have made a website for this. So how can we learn the code?
Yeah. So the solution at the end was built in an app called Streamlit, and Streamlit allow you to build a dashboard, interactive dashboard, either that can be hosted on your local machine, or you can host it on Streamlit's developer platform.
Okay.
If you go to the Streamlit website, it's probably, you can sign up for a free tiered account, And the tutorials it has on Streamlit are probably the best that I've ever seen in terms of documentation. It is very easy to learn Streamlit through their own documentation. The guy always who put this together for our particular project, he was a beginner in Streamlit. He'd never made a Streamlit app before, and as you can see, he's followed the documentation and made it his own, and it has been able to produce a very impressive platform at the moment. Again, he's working on this, and it's going to be a ever evolving development which he's going to use for his portfolio. But 2 weeks of reading the Streamlit documentation, he was able to put something such effective together as that. So if you check out the Streamlit website, you'll be very supported in in terms of the documentation and the community on there as well. Thanks very much for your question.
Sir, I wanted to ask a question, like Flask is like a little bit easier than Streamlit to learn. So can we use Flask for the front end part?
Absolutely. As Flask was the first initial sort of suggestion I made to the group. At the start, when we had a kickoff meeting, I wanted a dashboard to be created, hopefully with a machine learning sort of batch inference part to it. But unfortunately, we see that the data that is provided by the UK government wasn't robust enough. So we had to drop that part of the solution. Flask is fantastic. Flask is really good. It is arguably easier than Streamlit, but I think the Streamlit documentation is a little bit better, especially for beginners. So there was no real decision why we went for Streamlit and not Flask. It was just literally let the participants and the deployment lead pick what they want to do, and but there was no difference in there was no debate about it at all. We just picked what we first landed on, and it's been a great learning curve for everyone involved.
Okay, thank you, sir.
No problem. Has anyone got any other questions at all? Please raise your hand.
Yeah, 21 BAI 10022.
Hello.
Hello.
So I wanted to ask if it is feasible to make like 3 different models for like 3 different severities of like accidents in this case. Like we saw that different severities were like better in different ML models that you showed. So
Yeah.
Is it feasible in real life to make 3 different ML models and make them work together?
It is possible. It is possible. And you can also, we can stack models together. We can use the best way of stacking is using models that counteract each other's pros and cons. Using a random forest with a support vector machine classifier, for example, would be a great decision. However, we would run using this particular data set, we would run into the same sort of issues regardless of how many models we stack together or how many models we used in tandem. The problem is your model is only as good as the data you feed it. And as we've seen from deep diving from the EDA and from looking at the individual fatal cases, the data was reporting on weather conditions. It was reporting on junctions where the location of the accident. What it wasn't doing was trying to let the person looking at the data understand the nuance behind the accident severity. So why was this accident fatal? Why was it severe? And why was it slight? And there was no sort of clear definition in our data between that. It was just a feature that was there without any sort of correlation between any other features. When we done the feature importance part, using a model to try and see what features were important, what we could, perhaps reduce, get rid of and reduce the dimensionality of our data set, there was nothing that stood out. There was nothing really overwhelming that led to that told the story to land at the particular classification. So we would have the same issues there. The only solution that we can to improve our model is getting better data. And we would need data that probably wouldn't be available publicly. If we were working, as I say, if we were working for the Department of Transport in the UK, we would probably have access to the report that would give us some sort of nuance around the circumstances around the actual accident that happened. So, even it might even be in an open text format where a police report comes in and explains the situation. And in that case, we would have to use NLP to extract the information from the police report and correlate it to a fatal, severe and slight, and see how that would work. The data we have at the moment just isn't suitable because it doesn't tell the story of our classifications. But that's part of data science. It's a massively iterative process. Sometimes you can build a model that does the world, but and sometimes using machine learning isn't the answer. But it's all about experimentation, and that's what I wanted to show the beginners who came onto our project. There's no right or wrong answer. Just do your experiments and follow the experiments, follow the data that you get as an output, and you will come to a solution. Whether that is using machine learning, it doesn't matter. As I say, sometimes just good old-fashioned robust data analysis can answer the business question, and that's what's important. It's answering the business questions. That's how we get paid. That's how you add value, and that's what's most important. Thank you very much for that question. I hope that answered it.
Yes, sir. Thank you.
Any other questions?
I had a doubt.
Yep.
We being a bunch of children, juniors and seniors over here, I would like to know, as a beginner, how would you encourage and motivate a beginner to start their journey on this path of AI and machine learning? Being a beginner who does not know anything,
Yeah,
and who wants to learn.
the biggest sort of mindset that you need to start on a data science or machine learning journey is curiosity. That's the motivation. You have to be willing to learn every single day. Technical skills, can be quite difficult to have at the start, but as you the way I learn, I just need to jump in the deep end and be exposed to what I'm gonna learn, and that's how I've learned everything around data science and Python, SQL and whatnot, is just getting on there and trying it myself. However, you do need to be very curious about data. You need to appreciate the time spent mining, going through the data, pulling out insights, regardless of what data it is. It's the total attitude of being willing to learn. And when you move into a data science role, from the day you start a data science role to the day you die, you will learn something every single day. And that is something that if you don't like learning, data-centric roles aren't for you. The technology moves rapidly. The research into data science, AI, machine learning is, I think there was like 600 papers published every week. So it's just a constant learning curve. You can never master it all. It's impossible. There's just too much out there. If you look at like an MLOps pipeline, there's around 10,000 products in an MLOps pipeline that you could use. You cannot master all of them, but what you can do is learn something about the key ones, or if you learn something about AWS, if you become an expert in AWS, you will be able to find your way around Google Cloud. They're not too dissimilar, but that is me. So the main motivation, to answer your question, the main motivation from it to become from a beginner to an intermediate is just having the curiosity and willingness to learn and to learn every day. Like that is probably the biggest quality in a data science. And if you move into data science and you look at all the people who've been working in the role for 10 years, 20 years, they still remain very, very curious about everything to do with data. And it's that curiosity, it's that willingness to learn that will see you through to a very successful career. Hope that answers your question.
Thank you. That was quite insightful and quite motivating. Thank you. The
Cheers.
next we have 22 MIM 10125.
No, you can come off mute.
Are there any more questions? You can raise your hand and we'll unmute you.
Yeah. 10215 is back up. They have a mic issues. (10125), you can come off mute if you've got a question. No. No. If there's no more questions, it's been an absolute pleasure being here. And I've really enjoyed presenting our project. Omdina, if you haven't heard of it before and you are a beginner who wants to make a move into machine learning, data science, data analytics, whatever that may be, I would fully recommend signing up to Omdina and joining a local chapter and working on the solutions that they provide. There are projects of all skill ranges, from the very beginner to more advanced and expert level ones, so you can pretty much progress your career through this particular platform. I'm the lead of the Liverpool chapter, and our project has just ended, the one I've just basically gone through and showed you some of the coding and what we did. But we usually run a project once every 3 months. So if you sign up to Omdina, keep a lookout for a project that I'll be running. The next one will be a beginner intermediate as well. I'm not quite sure what the topic will be yet, but I'm sure it'll be a very in-depth and tricky one like the previous one. I do like to, not give everyone a very superbly easy ride. I like to have the beginners, look at the data and have to think about it. And, what I do sort of like about Omdina is that it is a safe space. You can ask whatever questions you want. There's no such thing as a stupid question, because all the beginners are there to learn. And if you don't know something, don't just, feel stupid asking it. Ask the question, and there's plenty of people around you who will be able to answer that question. I was the chapter lead, and I was supported by Salman Khalik, who's giving a talk, I think on day 3, around computer vision. He was my learning and development lead. So for the beginners, he also hosted separate calls to go through how to process data, how to feature engineer, and how to, start modeling and things like that. And that was very beneficial to all the beginners on the particular task. So yeah, please sign up to Omdina if you're serious about getting into data in the data industry, and I'll be more than happy to see you guys on my team working towards a common goal under my supervision. It'd be absolutely fantastic. But yeah, if any more questions at all, just before we call it quits, I imagine.
Thank you, Mr. Rich Gregson, for elaborating on all these concepts. With the end of such an informative session, I hope we learned a lot about AI and how it can make our lives simple and easy. I would also like to thank our sponsors, Zuno, Taskid, and TalkToSeniors.com for the support. Thank you.
Thank you very much. Have a good evening, everyone.
Thank you, sir.
Thank you, sir. Rest of the participants, please wait. There is going to be an email sent to you for the attendance. So please fill the form, the Google form, so that your attendance is marked for today's session. Please check your emails and do the needful. Thank you and have a nice day.